Well, hi everybody. We're going to start our next lesson on in calculus, and the topic we're going to be working on a while is finding the volume of solids of revolution. In this first video, I'm going to focus mainly on just trying to get the concept across clearly, I hope, and then in the next video we'll work through some examples of specific problems. But first, let's just get the idea down. Suppose I have like a hill of dirt or something like that, and I want to find the volume of that hill. Well, it's an irregular shape. You know, there's volumes formulas for things like cones and cylinders and spheres, but irregular shapes are hard to get. So what we're going to do is we're going to use calculus to try to get at this from a different approach. So let's say I had this, and let's say I want to imagine that I'm taking slices. So, like, this would be, if you think of the symmetry of this, see this parabola? You have an axis of symmetry here. When we slice these things, we're going to slice them perpendicular to the axis of symmetry. So that would be this way. Now, if I were to do that, if I were to carve this up into some number of slices, let me try to make them the same height. Well, except for that last one. So if this was slice 1, 2, 3, 4, 5, 6, 7, and 8, respectively, I could find the volume of the whole hill by finding the volume of slice 1 and adding it to 2 and 3 and so on. And I guess there's a number 8. And except for that very top one, they'd all have a very similar shape. Notice how, like, each one would have a circular top and just kind of a little curve on the bottom, almost cylindrical, but it kind of curves up a little bit. Now notice in how I'm adding these up, I could write this like this. This is the sum of all the v sub somethings, where the somethings start with 1 and end with 8. So I could say that this summation is approximately the volume of the solid. Well, I could divide that up into smaller pieces, right? So now instead of 8, let's say there's 16 of them. So now there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And I could keep playing this game and carve them up into smaller and smaller pieces. Well, the idea is if I let those thicknesses shrink down to 0, I would start getting a shape. So if each one kind of looks like this, each one of those, we'll call it a disc. It looks like a solid disc. These kind of bulge out. The thinner I make this, the closer and closer those sides get to being a line, right? So at first there was kind of a big spread there. When I cut them in half, it's not quite so much. And the thinner I get, the closer and closer that gets to a cylinder. So the idea is the limit, as we're going to call this the thickness of each slice. The limit, as the thickness goes to 0 of one slice, would be the volume. The volume of one slice as the thickness goes to 0 is equal to the volume of a cylinder. Right? The thinner that is from being a regular shape, if I let that thickness go down to 0, that becomes a very thin disc. It's cylindrical in shape. I don't know if I'm doing a good job or not getting that across, but that's very important because if I can get this small enough, and remember, the smaller these are, the more that will fit, so I'll have an infinity of them in there. Then the volume of each disc would be the volume of a cylinder, which is pi r squared h. See, now we have a formula we can use. That would be each one of these discs, and we're going to make them so thin there's an infinite number of these discs in the solid. So what I'm going to do is I'm going to think of the height as the thickness, and the radius would just be the radius of the disc. Radius of disc, right? This would be the radius, this would be the thickness, and pi is just pi. So if that's true, I'm going to switch to the black marker here, then the total volume of the solid would be equal to the sum of the volumes of all the discs. And that in turn could be expressed as the sum as k goes from 1 to infinity of pi times the radius squared times the thickness. And pi can be pulled out because it's a constant, so we could write it like this. Rad squared times thickness. Well, look at, we have an infinite sum, and this is starting to look like a formula. An infinite sum, remember, is, instead of this being approximately equal to that, this will be exactly equal to the infinite sum of pi times the radius squared times the thickness. So I know, like, how do we express this? How do we use functions? How do we use our calculator for here? That's all coming. The big thing is we need to see how you can carve something up in little slices, and then that's going to create our integral. Let me erase this, and let's do one from a sideways view. So let's say I have a shape that looks, I don't know, something like this. And let's make it, try to be symmetric. Let's make it more of a polynomial shape. So this will kind of look like a top on its side, and this would be flattened out, or like a Christmas ornament on its side. Notice that the axis of symmetry would be right kind of down the middle. So if I wanted to find the volume of this weird shape, I could imagine, like, let's say this was a radish. Looks kind of like a radish. I could take a knife and slice it into a bunch of different slices. And then I could find the volume of each slice, add it all up, and that would be the total. Now you might think, well, why would you want to do that? I know, like, that's more work to actually cut it up, but that's what we're doing conceptually. What you need to do, you have to imagine this axis of symmetry, or draw it, and we're going to cut it this way. Now I'm actually cutting it like all kinds of times, right? I'm slicing it, making all these different discs, but I'm just going to draw one because it will be ridiculously cluttered if I try to draw like tons and tons. This is one. Now to give it a little three-dimensional kind of feel, if you make an ellipse there, if you put a little line just kind of parallel to that, gives you the look of a disc. So let me do that again. So there'd be one here, so I draw an ellipse. Just put a little extra there. See, this would be one slice cut out of it. It looks like a coin. Now notice, I need to redraw this. I'm going to exaggerate the thickness. Really, these are infinitesimally thick, but I'm going to exaggerate this one. See, this has a certain thickness, and it has a certain radius, which I could go up or down. So this particular disk would have a volume of pi times the radius squared times the thickness, which I'll just use the formula. H is the thickness. Except notice this slice will be different than this slice, so I'm going to call this radius 1. This slice would be pi times the smaller radius, so let's call it radius 2. Radius 2 squared. And let's say they're the same thickness, right? So the h's are the same, the pi's are the same, but that radius is bigger than that radius. This would be one of the volumes. This would be a second volume. And I want to add all these volumes up to get the total. Now the picture is going to be very important when we get to our next lesson. We're going to use actual equations and make the equations up. But what we need to see here is we need to see the thickness. We need to see the radius. Some of these are going to be vertically oriented, like the one we just did. In which case, when I take a slice of that, see, imagine the axis of symmetry. And then when I cut it perpendicular to that, that'll create that kind of look. To give it a thickness, you just go like this. See, this has a thickness and it has a radius. So the volume of that one slice would be pi r squared h, where h is the thickness and r is the radius. But it's not just that one, it's an infinite number. We'd have to add that volume to that volume to that volume to this volume. And these radii are always changing, right? These are different radii. We use r because they're all radiuses, but they're all going to be different numbers. Okay, so that's the concept. We're going to leave that there. And then in the next video, which I'm actually going to shoot back to back with this, we're going to pull in actual functions. We'll get the equation and we'll work it out. All right, thanks.